It's time for another laboratory session. We're going to do a transient response of a cantilever beam that has a tip load on it. The beam is the same one we've looked at before, and it's sized to be something like an airplane wing for a fighter in terms of stiffness, but other people might want to think of it as a diving board. We'll reconsider the Newmark Beta method in a form used in MSc Nastran, and of course, as a large active corporation, they have input from the aerospace and the automotive community to try to doctor things up and make them more efficient and more robust. So there's some changes that we'll discuss. Then I'll talk about the problem statement, giving physical modeling and finite element modeling. We'll look at the Nastran data set, consider the results for two different accuracy levels, and the second is called the alternate solution, which will give a little finer detail to the response with smaller step size. I taught the Newmark Beta method for a number of years, and then was aware that the MSc Nastran version was also Newmark Beta, but it considered two previous time steps as well as the current time step. So at a national meeting one time, I asked Bob Harder, who was MSc Nastrans and still is their technical guru that seems to have a lot of corporate history remembered in his head, about this. And I said, hey, how come there are two time steps in the past rather than just one? And he said, well, this really was the same as Newmark Beta. And then he dug up some notes using a differential operator notation that proved that the two were identical. In order to convert that to something that's easy to teach, I think I like to tell people that it's like applying Newmark Beta to two successive time steps and then doing some averaging. I think this has the advantage of smoothing out the answers a bit. The algorithm won't look the same, and so I think people need to be aware then of this, the fact that it really is still Newmark. I'll call it modified Newmark Beta. And there are terms shown here that are at the time step n plus 2, that would be the current time, and the interpolation formula used current values, previous values, and two time steps previous. Likewise with this velocity interpolation here uses the current displacement and displacement two steps previous. Let's look at these relations in a more graphic way. Here I've got the displacement, velocity, and acceleration as a function of time. The starred quantities are the current values, which are unknown. Those are related by the equation of motion. So I'll draw one relation tying those together. Secondly, you have the relation, which is a interpolation formula relating the acceleration here, is this red star, to these three displacements. Let me draw a relation there, sort of a large swoopy law relating those. And then thirdly, we have another interpolation relation for velocity that says this velocity is related to the current and two times past displacement. So I'll draw another little loop here. Let me change the color now to green. Let me send this baby up here and around here and here like this. So that's another relation. So it's interesting how this process used by McNeil-Schwindler relates to different variables. Another useful modification helps in the case of massless coordinates. It's not generally appreciated, but often we have models that have a degree of freedom with no mass associated with it. And you'd like that to not suddenly accelerate with infinite acceleration. So the Elastic forces are softened somewhat by time averaging over 3 steps rather than using only the current step shown on the left. So this is a replacement concept here where we replace what's on the left with what's on the right. And it's just an equally weighted sampling of the current and the past 2 time steps. The same thing is done on the external force where it's averaged over 3 time steps looking backwards. Then when you put those terms into the equation of motion, you get the form shown here. We saw something like this in the conventional Newmark Beta method, and now this is what I'm calling the modified method. You might remember that all of these numerical integration methods based on Newmark would use gamma of 1/2, and that the most exact value you could use in terms of accuracy would be beta equals 1/6. That was the so-called linear acceleration method, but it's not unconditionally stable. Newmark proposed bumping that up to 1/4, which lies right at the boundary of a unconditionally stable system. MSc Nastran people bump it up a little bit more in order to give stability in nonlinear cases, and there are many of those in mechanics. The solution procedure is similar to the standard Newmark method. I'll write it out though so that you can see the notation used by MSc Nastran. Here is the stiffness for the assembled system, and sometimes I've called it a mechanical impedance because it has both stiffness and inertia effects in it. Here is a force on the right that is a modified force carrying forward some information from past time steps. The heart of the problem is to decompose this A2, and if you remember, we previously called that K hat in the general theory. So it's decomposed by the triangular factorization here, a product factorization, and the diagonal matrix is absorbed into the upper triangular matrix, and so that you use this form. Electrical engineers always speak of this form as the LU decomposition, but yet they do mean a symmetric problem in most cases, as we do. That problem is then set in this form where we recognize that there could be viewed an intermediate unknown here, which we might call y, and then we solve for that, and that's relatively easy since L2 is a lower triangular matrix. We can solve that in what's called the forward pass in a Gauss elimination sense, and then you back substitute into the definition for this vector y, which was this relation here, and that completes the solution. So the key steps are decomposition, forward pass, back substitution. Now, this might need to be done at every time step, certainly in a nonlinear problem, but if the system variables remain the same, you might be able to get by with only one decomposition of this A2 matrix. So it's a little bit problem dependent. In dynamics, actually we're a little bit luckier than statics, inasmuch as you only get a singularity when the system is missing inertia, damping, and stiffness forces all at the same time at any one degree of freedom. This is one reason that rigid body modes are not as much trouble in dynamics as they are in statics. You might call a degree of freedom where both mass and stiffness vanish a massless mechanism, and that would be trouble if there were no damping either. The Newmark method we're looking at here is unconditionally stable, so that it acts as a low-pass filter, and at worst it smooths the solution out too much. It doesn't make the solution get more jagged or to diverge monotonically or oscillate with growing oscillations that are numerically induced. So this is a good method. For many years it was thought too much trouble to integrate from non-zero initial conditions in the modal approach, but that's been installed for some years now, perhaps 5 or 10 in Nastran, so that now it's possible to integrate equations that have non-zero initial conditions either in direct integration methods or modal integration methods in Nastran. The assumption, however, is that those initial conditions are zero if you don't say otherwise. And that makes sense. So there wouldn't be any other way to do that. I got a kick years ago about this process when Vern Overby, at the time with A.O. Smith, drew some clever cartoons about the difference between, at that time, the integration of modal solutions and direct integration. And he presented these at a national meeting, much to the delight of everybody. But this problem now is very routine. Nastran also post-processes by smoothing out velocity and acceleration. Once you've done the complete integration in time, you have this set of numbers, a table of numbers. Then you can smooth your velocities in any instant of time n by averaging both future time and past time. So it's kind of a central differencing that can be done. So think of this as a post-processing step to smooth out the data that are printed out at the end of the run. So that's done with both velocity and acceleration data. And this again is a slight modification, although a very slight one, of the original Newmark method. We saw earlier that there are two easy ways to interpret error in a direct integration process, and one of them is to look at a harmonic oscillator in terms of the frequency that you obtain for free oscillation, and the other is to see whether there's any decrement in amplitude and or an amplitude decay. Now, we found that the Newmark method did not introduce artificial damping when you picked the gamma to be 1/2. Therefore, the only error measure that we're interested in is the frequency that's calculated. There's an excellent formula given in the MSc Nastran documents that shows the frequency error for this method. And it's given as the calculated frequency by a numerical method for a spring mass system compared with the exact value. So you'd like this ratio to be unity, but the numerical integration tends to slow down the frequency. It tends to smooth by this low-pass approach. And here is one form using the exact frequency in radians and then the time step. But I find the better formula, this one here, in which you subtract off according to the number of time steps per wave. This latter expression is relatively easy now to calculate, and if you pick numbers such as n equals 5, let's say, so that there are 5 numerical samplings per sine wave, then this becomes roughly 10 over 50, and that's roughly a 20% error, because you'll be knocking off 0.2 from this unit value and getting 0.8 of the desired frequency. If you take 7 samples per wave, then this becomes roughly 10 over 100, and that gives you 10% error. Finally, if you take 10 samples per wave, you get roughly 10 over 200, which is a 5% error. So I find those three cases to be enlightening. You can see why, for engineering accuracy, many people would like to have 10 sample points per sine wave. And that means that your time step for your integration would be 1/10 of the period, the natural period of the oscillation that you're trying to study. From the previous discussion, I think you can see that it's important before you do the numerical integration to recognize what the dominant response frequency of your structure is. Then you can choose an appropriate time step that will capture that behavior. Unfortunately, a lot of structures have multiple natural frequencies and the potential to respond with each of those frequencies. We'll pick such a structural dynamics case here. It's a cantilever beam that we've studied before, and its first two frequencies, roughly speaking, are at 9 hertz and some 56 or 57 hertz. So we can see that our time steps could be chosen to resolve either only the fundamental response or perhaps the first two modes of vibration in the response. So we'll model this slender cantilever beam as used previously, and we'll put a tip load as shown. So this is a sawtooth, a single sawtooth wave with a ramp entrance to the load reaching 10,000 newtons at the peak, and then an abrupt drop off. Now, for people who know shock response of structures, and if you know linear structures, you know that a sudden drop off of force is just as bad as a sudden rise in force. So it's as if you have removed this 10,000 Newton load by suddenly applying a minus 10,000 Newton load. Our beam will have no damping. It will be initially at rest, and then we want to find motion for some subsequent time. And we'll start out looking at the first half second of response. Now, because this beam vibrated in its fundamental mode shape at about 9 hertz, that means in half a second we'll pick up 4 or 5 oscillations. And we'd expect this beam to be shaken and do some kind of rattling motion here if we apply that load at its tip. Now let's look at the physical modeling that we need to carry out this laboratory. We'll use the simple beam theory due to Euler-Bernoulli and Navier, and we'll constrain our motion to lie in the XZ plane. That means we're not interested in the axial, torsional, and the XY flexural motion, so we can constrain those variables. From previous work, we have found that the first frequency of natural vibration is 9.2 hertz and the second is 58 hertz. We're somewhat interested in what the response will be and try to predict this ahead of time so that we can take time steps that are fine enough. The half period of the load, if you think of it as a half sine wave, would be 2/10 of a second. If this were continued with positive and negative lobes of force, that would have an effective frequency of about 2.5 hertz. That's below the first natural frequency of the system, and I would think would tend to excite the first natural frequency more than the others, were that actually applied in that oversimplified way of looking at it. On the other hand, the drop-off, the sudden drop-off of force will have a shock effect on the system and excite all of the frequencies. Because the load is applied at the tip, though, it will be very effective in a spatial sense in exciting the first mode. So we'd expect quite a bit of first mode response out of this system. Accordingly, we'll take a first run with a time step of 1/100th of a second, and that will give us about 10 sample points per wave of the first elastic vibrational mode in terms of the time history. And then we'll follow with a second run where the time step will be 0.0006. This will turn out, if you figure out the sampling rate, to give you about 25 samples for each wave of vibration of the second mode frequency. So that should be enough to capture the behavior of both the first and the second mode. Our finite element modeling will be done simply as it was before, using two bar elements. We're going to use a direct integration rather than a modal integration. The load has to be characterized, and we do that in a plot as shown below, where we have 5 points that identify it. We have those that play out the zero force region, then the two nodes that or 2 points here that define the ramp, and then the 2 data points that are coincident in time that define this drop-off. Finally, a zero load section. MSC Nastran has been set up that when there are 2 such forces at the same instant of time, it will choose an intermediate point if you happen to have a time step that lies directly on that precipitous drop. You can see that that's a slight smoothing effect then that would make this actually smooth depending on your time step. We're expecting to see a response something like this. I'm going to actually use a small commercial plot package called Cricket Graph to get that plot. Let's look at our MSC Nastran data set. Here's a file management statement that tells the program where to put the output, which we can post-process. The executive control statements establish the ID of the problem. We've allowed 5 minutes, which is way more than we need. SAW 109 is the direct transient integration package. Under case control, we have the title and subtitle. We ask for all displacements. The dynamic load number 20 refers to another card below, as does the time step. And those both point to bulk data entries. Here's our bulk data set. Here's our post-processing file. We're going to use coupled mass. As in our previous models, we'll constrain the degrees of freedom at the wall with this permanent embedded constraint set. Here we're also constraining the outboard degrees of freedom that are not needed for our flexural motion in the XZ plane. Here are the bar definitions for connectivity, pointing to property here. The property in turn points to the material here. And we have steel properties. You remember the density is rather low in the when we use millimeter second Newton systems. Here's our T-load card that was mentioned above. It in turn points to a D area, which is the magnitude, and to a table that shows the time dependence of our force. At one time I was rather puzzled why we used a card labeled area for a magnitude, and I think that comes from the aeronautical usage where you have aerodynamic surfaces exposed to pressures, and so it's appropriate, and that's the way I remember it, that you think of an area exposed to a load as somehow being responsible for the magnitude of the load. Notice that we have on the third grid point in the third coordinate direction 10,000 newtons as our magnitude. Then the table of points carry the shape of the disturbance, and the magnitude is pretty much carried by the D area card. time step down here was pointed to from up above in case control as 30. We're going to ask for 60 time steps with 1/100th of a second each, and ask for all data to be printed out without skipping any. In this figure, I'm just reviewing which cards are new to us. We have our solver here, the time step card up at the case level, then the time step card down in the bulk data. And I've already discussed how we had the number of time steps, the time increment, and then the skip factor. There's some question in my mind about this one in terms of skipping. If you didn't want to plot every point, then why would you calculate them? Because omitting those intermediate points in the plot is also a low-pass filtering operation. So other things being equal, I'm not certain clearly why you would ever pick anything other than 1 here. Now, I'm a little bit naive on this, and maybe there are times when you would. But it seems to me that whether you skip the intermediate time steps in calculation or whether you skip them in plotting, in either way you would be acting as a low-pass filter and smoothing out the answer. And it would be more consistent to do the calculations to the same accuracy as you're plotting. So I'm being a little bit ornery on this term here. I always put 1 anyway. Then our transient load card here, calling out the D area, which is the magnitude card as we had said, and then the table D1 over here for the shape and then the type of load involved. Let's look at the sorted bulk data here. And no new surprises here, I would say. Let's look at some of the tabular data for the response of the tip in particular. That's this column here where we're interested in the translation in the 3 direction for the node number 3. This is for short time here up to 0.2 of a second, and in that time we see we've only reached 19 millimeters of displacement. So we're at this point well within the range of the linear Euler-Bernoulli beam theory because this displacement is substantially less than the depth of the beam. Let's follow this motion out a bit farther to see whether there are other larger amplitudes reached. And here we are at higher times approaching the 0.6 of a second that I integrated to. And in here you see that at one point we have here 34.7 millimeters. Now that's still substantially less than the depth of the beam, so this ought to be reasonably accurate within the Euler-Bernoulli beam theory. Now let's use the Cricut graph plot package to show us our response. Up until time of 1/10 of a second, the load hasn't been applied. Then when it's applied, notice that the system is able to respond rather well and also rises in somewhat of a straight line, but modified by this oscillation. It will turn out in retrospect that the system is relatively stiff on that part of the loading cycle because the first natural frequency is several times higher than the period of the load application, at least on the ascending ramp. Once the load suddenly drops off, however, you then excite all frequencies in the body, and here what we're seeing is a natural ringing of this system in its fundamental mode. Notice that we're picking up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 time steps per wave, and that should give us rather good accuracy, perhaps 4%. It took 10 samples to give 5% accuracy, if you remember, and this is better than that. So we're rather well characterizing the response in the first normal mode of this cantilever beam. A slightly better figure can be obtained by removing the symbols. This somewhat obscures the fact that we don't have enough data points, since we only see the sharp breaks between the data points as straight line segments, but you get a general idea. All told, though, it appears that we're not able to resolve the really fine detail in this. These truncated peaks as here, these rather sharp truncations here show that we're not following the actual process at the extreme part of the motion. So this leads to a desire for a more accurate solution shown in the following figures. I'd like to redo this problem using a smaller time step so that we can resolve the response of this beam in its second mode. We'll call this an alternate solution. The time step is reduced to 0.0006 seconds. If you look at the second mode, which has a frequency in the neighborhood of 60 Hertz, then this will allow about 25 time samples per cycle of motion. This will be enough to really nail down the behavior of the second mode response, but it's not enough to really capture the third mode response. So we're working into this gradually. Let's shift the load pattern to the left 1/10 of a second so that we don't spend so much time integrating the system when there's no load on it. That was that 1/10 of a second dead region previously. To do that, we just need to redefine the table D1 entries to show the 5 points that are shown. Then on the time step, we'll ask for more time steps and with a smaller time step magnitude. When these results are plotted, they are very revealing, and they do pick up free vibration in the second mode as well as in the first. When the beam is being loaded, and we know the mean response, if it were a static response, would follow something like this, we see that not only do we get the first mode oscillation about that mean static response, but we get the second mode oscillations, if you can see those little bitty fellas in there. And both of those effects carry on, although as you can see, once you give the large drop in force, which in effect is the same as shocking the system with a large sudden negative load, that primarily excites first mode behavior out here, with some second mode behavior on top of that, which is the smaller detail. So this is quite pleasing to see this kind of time integration. I do feel that such numerical integration is the next thing to doing an actual experiment, because you watch the system's response in time. I think if you're attentive to the details of the time step size, and if you understand the Newmark integration, this can really be a strong tool then in your technical bag of tricks. Up to this point in this course, we've been studying what I call passive nodes in the finite element analysis. Now I'd like to change direction and consider what would happen if there were a control system that introduced forces at these nodes. And these forces are not just external, but they are internal, and they intervene between the degrees of freedom, say on a left-handed element and a right-handed element that join at a common node. This is a new idea and something I'll have to explain in more detail when the time comes. So we'll look at active nodes, and then I'll take a specific system. We'll look at a fly swatter, a robotic fly swatter, and then I'll go through 3 problems in a problem session. Let me review the common usage of our nodes in the past, and then we'll gradually work toward the active node. In this figure, I have 2 usages that we have already encountered. The most common one is when the node is considered to be welded, and then it's pretty easy for people to appreciate that under load that this body would follow some smooth curve. They don't expect to see a kink develop at either of those nodal points. Interestingly, if you go to the next more difficult step, namely a cantilever beam which has a kink in it at the outset, and then you put a load on that, there are many people who, for some strange reason, might expect that this joint here would then develop a different angle than the one shown currently. Currently I'm showing about 160 degrees there, and so if I drew an included angle here of 160 degrees, and you ask students would that open up upon application of the load, they would say sure, it might be 170. Wrong. That angle cannot open. It's a weld, and you can't get any accumulation of a finite change in angle at a point. Well, maybe that's a little bit of a difficult concept, but people usually follow that. I know that on my hollow octagonal electric pole arm, that when I asked the students to make a plane of symmetry here and then give me the boundary conditions as you model